In this video, we're going to be talking about scientific notation. We're going to talk about what it is and why you would use it, what it looks like, how it works, and we're even going to cover all of the rules you'll need to manipulate scientific notation. Plus, we'll talk about some specific questions like significant figures. Well, the first thing we need to understand is, what is scientific notation? Well, it's just a shorthand way or an easy way for us to express very, very large or very, very small numbers. And those numbers can either be positive or negative, but it basically gives us a way to express huge numbers or really tiny numbers without writing out a huge string of numbers. So, for example, scientific notation could help us abbreviate numbers like these. So we have a very large number, 96,300,000, and we have a very small number, 0.00000023. So both of these numbers, a very large number and a very small number, can be easily expressed in scientific notation. So how does scientific notation actually work? Well, let's go ahead and jump into two examples, one with a very large number and one with a very small number. So when we have numbers like these, when they're very large or very small, sometimes it's going to be easier for us to express those in terms of scientific notation. And even these, you might think, well, I can just count the number of zeros and I kind of have an idea of what this number is. But imagine that we added maybe 100 more zeros to the end of this number, or 100 more zeros in the mix of all of these zeros here. It would obviously be extremely tedious to count how many zeros you have in each number to figure out exactly what that number is. But if you instead write the number in scientific notation, it'll be a lot easier and faster to identify the value of that number. So here's what it looks like to change numbers like this into scientific notation. First of all, scientific notation is always made up of two pieces, and those pieces are multiplied together. So we're going to have the product. There's the first term, which is always going to be a decimal term, and the second term is always going to be 10 raised to the power of something. So we're going to have a decimal here multiplied by 10 raised to an exponent. That will always be the case for scientific notation. The scientific notation will always be in that form. So here's what you want to do to change a number like this into scientific notation. We want to recognize here that we really have a decimal point here at the end of this number. You could think of this as 20 with then 9 extra zeros and then a 0.00, right? We have the decimal point, and we could write as many zeros here on the end as we wanted, but our decimal point is right there. What we need to do is move that decimal point over until it's right after the 2. So if we do that, let's count how many places we move it over. We move it over 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 spots until it's after the 2. So because we moved it over 10 spots, we're going to have here 10 to the 10th power. If we had moved it over 12 spots, we would have 10 to the 12th power. If we had moved it over 8 spots, we would have 10 to the 8th power. So this exponent is how many spots you move your decimal point. Now for our decimal value, the first number that's part of our scientific notation, we just take everything that's left in front of the decimal point, which is just a 2, and any non-zero digits that are left after the decimal point. But we don't have any non-zero digits after the decimal point. These are all zeros. So we just have 2 times 10 to the 10th. And this is the scientific notation for this original huge number. Now let's do the second example here, and then I want to talk about a couple of important points about what we're doing about this scientific notation process. So the same thing here, we have our decimal point right here. We need to move it over until it's right after the 3. So how many places am I moving it over? Well, I just count again. So I go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, until I get here right after the 3. So because we move the decimal over 11 places, we get 10 to the negative 11. Now this is one important point before we go on. When you move the decimal from the right to the left, so when we moved the decimal, we went to the left, and you can even draw an arrow in the direction that you're going to help remind you. When you move the decimal to the left, your exponent on the 10 will be positive, which is why we had the positive 10. When you move your decimal to the right, then the exponent on your 10 will be negative, which is why we wrote negative 11. So positive when you move to the left, negative when you move to the right. So that's one thing to remember. And then what do we put for our decimal term here with this number? Well, we could write here after the new decimal point a bunch of imaginary zeros. And then for the decimal, which non-zero numbers do we have before the new decimal or to the left of it? Just the 3. We don't have any non-zero numbers to the right of it, so we just write 3 here, and 3 times 10 to the negative 11 is the same number as the value we were given here. Now let's go ahead and answer a few questions. First of all, why did we move this decimal over until it was just after the 2 here? Why did we move this decimal until it was just after the 3 right here? Well, the reason is because this decimal term, just like the second term, always follows a pattern where you have 10 raised to a power, and the power is how many decimal places you move to the left, giving you a positive exponent, or how many decimal places you move to the right, giving you a negative exponent. This decimal term at the beginning of scientific notation also follows a pattern. The pattern is that the number before the decimal point, so you could think about this as 2.0, or this here as 3.0. So the number that is in front of the decimal, in this case 2, in this case 3, that number must be between 1 and 9. So it can be 1, 2, 3, 4, 5, 6, 7, 8, 9. It cannot be 0, and it cannot be 10 or greater. So in this first problem, if I had stopped with my decimal point right here, then what I would have had to the left of it was 20. But I can't have 20 to the left of my decimal point because I need that number to be between 1 and 9, which is why I had to bring the decimal all the way over here. What about if I had taken the decimal one more spot and moved it here? Well, in that case, I always take the number to the left of the decimal point to be my decimal term. It would have been 0 because there's just an implied 0 out in front here. So I would have had 0.2 for my decimal number, and I can't have that. Remember, I can't have 0. I have to have a number between 1 and 9. So that's why you always want to bring the decimal until it's just after the first non-zero number. So the same thing with this small number here. We brought the decimal to this particular spot because it was right after the 3, which means that we can then say 3 point right here for the decimal number. If I had only brought it to here instead, my decimal number would have been 0.3. But I can't have a 0 in front of the decimal, so that wouldn't have worked. And if I would have brought the decimal to this spot, one more, then I would have had 30 in front of my decimal point, and that's not acceptable either. So that's why we had to come right here. Now, these were particular cases where I ended up with 2.0. So I ended up with the decimal right here, which left me with 2.0. And I ended up with the decimal right here, which left me with 3.0. So when you have 0.0 for your decimal number, you can drop that 0.0 from your scientific notation, and that's why we just said 2 times 10 to the 10th, or 3 times 10 to the negative 11 instead of 2.0 and 3.0. It's unnecessary to write the 0.0 if that's what you have. But let's say instead of this 20 and then the 9 zeros, what if we had 21 and then 300 and then our 6 zeros? So for a number like that, again, we need to move the decimal point to this spot right here so that we have just a 2 in front of this new decimal point, not 21, which would be greater than 9, and not 0 if we move the decimal point all the way in front of the 2. We need that number between 1 and 9. So we move it to this point. So then we have 2 in front of the decimal point and a 1-3 after the decimal point. So if we were going to write this in scientific notation, we would actually write it as 2.13 times 10 to the 10th. And the reason is because we keep our 10 to the 10th because we still moved the decimal point the same number of places, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 to that spot. So we still have 10 to the 10th, but then we want to keep our non-zero numbers as part of our decimal. So you can see here that we have the 2.13, and we want to keep that here as part of our decimal. But make sure that you only ever keep the non-zero numbers. So we would never keep 2.130 because we never need to write an extra 0 on the end of our decimal number. And we never need an extra 0 on the beginning, like 0.2.13 or 2.130. We don't need those extra zeros. We only need the non-zero numbers. So we want 2.13 times 10 to the 10th. And then same thing here, if instead we had all this the same, but then 315 right here, we would have written that as 3.15 times 10 to the negative 11, keeping those non-zero digits as part of our decimal number. Now, before we go forward, let's say one quick thing about significant figures. We just talked about keeping the non-zero numbers as part of the decimal. So here we kept 2.13 and here we kept 3.15. Well, when you hear about significant figures as it relates to scientific notation, the number of significant figures in the scientific notation is given by the number of non-zero digits that you have in your decimal. So here we have 2, 1, and 3. So we have 3 significant figures. And here we have 3.15. That's also 3 significant figures. But here where we had 3 times 10 to the negative 11, we only had the 3. Remember, we don't write the 0.0. And even if we did, that's still a 0 digit, so we wouldn't count it. So here you just have 1 significant figure because you have the 3. And here you have 1 significant figure because you just have 2 times 10 to the 10th. So significant figures is the number of non-zero digits that you keep inside of your decimal term. Now, why is scientific notation useful? Why do we actually use it in math? Well, we briefly touched on it earlier, but the reason that it helps is because when we have a large string of digits, like here in this number, whether the number is very large, or here in this number when the number is very, very small, scientific notation gives us a standard to know how many digits we're dealing with. So here it's somewhat easy because we have the commas, so we can say 3, 6, 9, 10 zeros, and we could maybe know what that number is. But here, if we just see this number, we actually have to go in and look in close and count these zeros without any commas. There's no quick way to do it, so we actually have to get in really close and say 1, 2, 3, 4, 5, 6, and hope we don't mess up on the number of zeros to figure out the place value of this 3. So really, really, really small numbers or really, really, really big numbers can present a huge problem, like we said before, especially if we were to add in 100 extra zeros here. Now it doesn't really matter that we have our commas. We're still stuck counting 3 zeros at a time, 3, 6, 9, 12, 15, counting up to 100 zeros to try to figure out what this number is. Or this number right here, if we added 100 zeros, we'd be counting forever. So the way that we get around that is with scientific notation, because this gives us a standard to tell us how many places, how many decimal places we're actually dealing with, and we can get a much clearer picture, much more quickly, about the exact value that we're looking at. And that becomes really, really important to people who deal with these kinds of numbers. So for example, if you're an astronomer and you're trying to figure out how far away some body in space is from Earth, it might be millions and millions and millions and millions of light years away, and you can imagine how big of a number you'd be dealing with. Without scientific notation, it'd be almost impossible to work with a number that large. Or maybe if you're a scientist who deals with something at the molecular level or the atomic level, and you're trying to measure the width of an atom or the width of some other part of a molecule, or you're trying to measure the size of part of a cell in a human body or something like that, you're going to be dealing with a number that is extremely tiny. And without scientific notation, you don't have a clear, quick, easy way to express the exact value of that number. So that's why it's so important that we understand how to use scientific notation and how to use it to represent very large and very small numbers. Now, one last thing we want to say before we talk about the rules that you use to manipulate scientific notation. You can also use scientific notation with negative numbers. So if instead here we had been given a negative number and a negative number, your entire process for converting that to scientific notation stays exactly the same. The only difference is that you just have a negative sign out here in front of the decimal number. And same thing here, you have a negative sign out in front of the decimal number. So this number in scientific notation, if it were negative, would just be -3 times 10 to the -11. So nothing else changes besides that negative number. Now let's talk about the rules of scientific notation. We'll go ahead and start with addition and subtraction, and then we'll talk about multiplication and division with scientific notation. So for both addition and subtraction, you're going to follow the same process. The first thing you want to do is you always want to convert the powers of 10 so that they're equal. So you'll notice here that we have 10 to the -2 and 10 to the -4. We need to somehow make those exponents the same before we can go ahead and do the addition. So that's our first step. So how do we do that? Well, we can do it either way. It never matters, so just pick whichever way is easier for you. We can either make 10 to the -2, 10 to the -4, or we can make 10 to the -4, 10 to the -2. And the way that I like to remember this, again, it doesn't matter which one you do. Let's go ahead and do the second one here. So let's change the 10 to the -4 to 10 to the -2. So this can get a little tricky, but here's how I like to think about it. And this may even help you if you want to go ahead and use this trick. So first of all, just think about the number line here. I want to change this -4 into a -2. So if I draw my number line and I have 0 here, I know I have -4 here, and I know I have -2 here. I'm going to be starting at -4, and I'm going to be going here to -2, which means I'm moving to the right. I am increasing the exponent. My exponent is getting larger, even though you might think it's getting smaller because we're going from 4 to 2. Because we're on the negative side here, going from -4 to -2 is actually increasing the value of the exponent. So if I'm increasing the value of the exponent, that means that I have to decrease the value of the decimal term in order to compensate for that change. So I'm actually going to change the -4 to a -2, which means that I am moving 2 units from -4 to -3 to -2. So that means that I have to move the decimal point 2 units to the left in order to decrease the value of my decimal. So let's go ahead and scooch this over a little bit here and say plus. Let's go ahead and write a couple zeros out in front. So I need to move this decimal 2 places since I changed the exponent by 2. So 1, 2, and my new decimal needs to be right here. So I increased the exponent by 2, which means I need to decrease this number. I need to make it smaller. And obviously changing it from 3.2 to 0.032 makes it smaller, decreases it. And I moved the decimal 2 places over. Now my powers of 10 have the same exponent. They both have a -2. So when I add my scientific notation, I'm going to keep my 10 to the -2 the same. And that's always the case. So once you get these equal to each other, you always just keep the exponential term, 10 to whatever it is, exactly the same. That doesn't change. So you keep that there. And then, now that everything's the same, you just have to add the decimal term. So we just have to simply add 4.215 to 0.032. When I do that, I get 4.247 times 10 to the negative 2, and so this then is the sum of these two separate scientific notations, and this sum is actually equal to this scientific notation here. So that's how you add scientific notation together. And then subtraction is actually really similar because, again, we just convert the exponents on the tens until they're the same, and then we'll just be doing simple subtraction of the decimals. So this time, let's take 10 to the 4 down to 10 to the 3. And remember, it doesn't matter which term you attack. Let's just go ahead and pick this one. So again, from our number line, we're taking 4 down to 3, which means we are decreasing this exponent. 4 down to 3, that exponent is smaller. So if we're decreasing the exponent, that means we need to increase this number. We need to make it a larger number. So in order to make it a larger number, we can't move the decimal place to the left because that would change 8.97 into 0.8, which would obviously be a smaller number. We need to move it over one spot here to make it 89.7, which is clearly a larger number than 8.97. And we moved the decimal point just one place because we're decreasing this exponent by 1 unit from 4 to 3. So we change this to 10 to the 3rd. We decreased the exponent by 1, which means we need to increase this number by moving the decimal one place to the right. Now we just do our simple subtraction of 89.7 minus 2.62 gives us 87.08. And remember, we always keep the 10 term the same, so we say times 10 to the 3rd. Now, here's something interesting. So in this previous problem, we had no issue because we ended up with 4.247. And remember, in front of the decimal point here, we always want a number between 1 and 9. And 4 was perfect. We had 4 between 1 and 9, so that decimal term was perfectly acceptable. But here, we have 87 in front of the decimal point, which we definitely can't have. We need this to be between 1 and 9. So even though this answer is a correct answer for the difference between these two scientific notations, we need to put the final answer in standard form of scientific notation. So in order to do that, we need to move this decimal point back right here so that we have 8.708, and we then have a value in front of the decimal that's between 1 and 9. 8 is between 1 and 9. So if we need to move this 1 to the left, that means we are decreasing the decimal term because we're going from 87 to 8.7, so we're definitely decreasing that number, which means we need to increase the exponent on the 10. And because we move the decimal point one spot, we need to up the exponent by 1. So what this becomes then is 8.708 multiplied by 10 to the 4th. Now here's another important point. Remember that our decimal term, we want to include only significant figures, non-zero digits. And notice that we have a 0 here in our decimal term. We don't want that. We don't want to include that 0 term ever. So the way that we do that is we round. So we have 8.708. In order to make this 0 not a 0, we can round using the 8 right here. Because this is an 8, we round up the previous digit or the digit in front of it. So this 0 rounds to a 1. So this gets rounded to 8.71 times 10 to the 4th. This then is standard scientific notation because we have a value here between 1 and 9 for our decimal term. We have no 0 digits in the decimal, and we have our perfect 10 to a power here. So this is our final answer for the difference between these two scientific notations. Now, what about for multiplication and division? Well, these are actually pretty simple too. Whenever we multiply our digit terms like normal. So we just take 3.4 times 4.2, and that actually gives us 14.28. And then we multiply the 10 terms together. So 10 to the 6th times 10 to the 3rd. When we do that, we always add our exponents together. So 6 plus 3 is 9, so we get 10 to the 9th. So remember, multiply the decimals and then add the exponents. So we get 14.28 times 10 to the 9th. But then, like in the last example where we had the subtraction, we need to remember always to keep only one non-zero term in front of the decimal point. So because we have a 14 in front of the decimal point, we need to move our decimal point until it's right here so that we have 1.428. But because we changed this from 14 down to 1.4, our decimal value went down, it got smaller, which means our exponent here needs to go up. It needs to get bigger. So 9 needs to become 10. Because we moved the decimal 1 point, we go up by 1 from 9 to 10. So this then is 1.428 times 10 to the 10th. And we have all significant figures here because there are no zero digits in our decimal. And so everything is perfect, 1.428 times 10 to the 10th. Division is similar. We divide the digit terms, so we say 6.4 divided by 8.9. And that actually gives us 0.719101112. And then we subtract the exponents on our 10 terms. So we say 10 to the 6th divided by 10 to the 2. We subtract the exponents starting with the first one. So 6 minus 2 is 4. So we have 10 to the 4th. And then just like with multiplication, we need to make sure that our final answer is in standard form for scientific notation. In this case, it's not, because we have a number that's not between 1 and 9. We have a 0 here in front of the decimal when we need it to be somewhere between 1 and 9. So in order to correct that, we need to move the decimal over one spot so that it's right here, and we have 7.19. 7.19 is obviously between 1 and 9, so we'd be okay that way. We're then increasing the decimal number from 0.7 to 7 something. So because we're increasing the decimal number, we have to decrease the exponent here on the 10. We moved the decimal one spot to do that, which means we need to decrease the exponent by 1, the number of spots that we move the decimal point. So we need to decrease this down from 4 to 3, and we can say then that we get 7.1910112 times 10 to the 3. But remember, we never want any zero digits, any zero values inside of our decimal number. So what we do is we look at what's after the 0 here, and we can see that we have a 1 after the 0, which means that this will round down just to 0. So that would leave us with 7.1910, but we don't want that trailing 0. So for significant figures, we just end up with 7.191 times 10 to the 3rd. The last thing I want to talk about with scientific notation is how to quickly compare scientific notation to see which is larger and which is smaller. And this is a really simple two-step process. So if we look at two numbers written in scientific notation, all we have to do is compare the exponents on the 10 terms and see which one is larger. Whichever exponent is larger will be the larger actual number. It doesn't matter at all what the decimal number is. All that matters is which exponent is larger. So in this case, because 12 is larger than 11, this number here is automatically larger or greater than this number here. And that's all we have to consider, is just which of the exponents is larger. Whichever one is larger, that means that scientific notation number is bigger than the other one. But what happens when the exponents are the same? So let's say that this here is a 12. Now which scientific notation is larger? Well, we look at the exponents and we say they're equal, so I can't tell. Well, if the exponents are equal, then you move on to step 2, which is that you compare the decimal numbers to one another. So then we move on to step 2 and we say, what's larger, 3.2 or 4.7? Well, 4.7 is larger, so because the exponents were equal and 4.7 is larger, now this number on the right is greater than this number on the left. So it's just those 2 steps. Look at the exponent first. Whichever exponent is bigger, that scientific notation is larger than the other one. Or if the exponents are the same, then move on to step 2 where you look at the decimal numbers and compare those to each other. Whichever one is bigger represents the greater value in scientific notation. And of course, you could flip this around too, and if you're asked which number is smaller, you would just compare the exponents. So again, here, if I had 11 here and I'm asked which scientific notation is smaller, I do the same process. I compare the exponents and I say this exponent of 11 is smaller than the 12, which means this number in scientific notation is automatically smaller. So that is the smaller one. Or if the exponents are the same, again, this is 12. Now my exponents are the same. I again move on to my decimal numbers and I say 3.2 is smaller than 4.7. So the number here on the left with 3.2 is smaller than this one, and I can conclude that this number is smaller. So whether you're asked to figure out which number is larger or which number is smaller, you're going through the same process of comparing the exponents, and then if those are equal, comparing the decimal numbers. I hope that video helped you, and if it did, hit that like button, make sure to subscribe, and I'll see you in the next video.